Alrighty, hi everyone. Hope everyone's having a good Monday after their break. Um, Welcome to your review session. If you're in Dr. Altamos's class, right, your exam is on Monday, Monday is on Wednesday. So the next time you go to class, you will be taking your exams. This is like your last little bit before you take your second exam. And then if you're in Dr. Altman's class, you will have class tomorrow, and then I will also be having my like normal review session on Wednesday. So you can have this and the next review session for any of your last minute questions. But with that, I will open the floor to people's questions. Feel free to ask whatever you would like. If you have your own questions, if you have mock exam questions or anything like that, the floor is yours. You can just put it in the chat or take yourself off mute. Okay, so I have a question about intermolecular forces and then IMFs, or sorry, those intermolecular forces and then polar versus nonpolar. So we will start over there. We will start there. So let's first start with polar and nonpolar. So if we have a polar compound, what does it mean to be polar? What is involved, or what do we have in a polar compound? Good. So we have a couple good answers here, right? We have asymmetry, and we have differences in electronegativity. Oops. Right, differences in electronegativity. Based on the trend of our periodic table, as we go left across the periodic table, electronegativity increases. And as we go down the periodic table, your electronegativity is going to decrease. So your most electronegative atom is fluorine. Whenever you're given something where you do need to determine if something's going to be polar or nonpolar, they will also give you those values. But fluorine is your most electronegative atom. Oxygen is like your second most electronegative atom. Okay. So if we have a polar compound, that would be something like carbon and oxygen, right? Or oxygen and hydrogen, right? These are both polar molecules, which means we have a dipole moment. We're going to draw an arrow towards the more electronegative atom, right? So in the case of carbon and oxygen, oxygen's more polar, or sorry, more electronegative, so it gets that arrowhead of the dipole moment. And in the case of oxygen and hydrogen, right, we're going to point it towards the oxygen because oxygen's more electronegative. And then the least electronegative, or the more electropositive, is going to get that plus sign. So I think this looks like a positive, and that's where the plus goes, and you're pointing the arrowhead towards the thing that's more electronegative, where it's going to be more polar. All right, so that's going to be a polar compound. If we have nonpolar, that just means we have no difference in electronegativities. So that's going to be some examples of the same thing, like carbon-carbon, right? You have the same element that's not going to have a polar compound, or maybe fluorine and fluorine. And then the one case where it's the different elements, but still nonpolar, is going to be hydrogen and carbon. Those have similar electronegativities, where this is still a nonpolar bond. Where it becomes into play is something's going to be polar or nonpolar in terms of the molecule, right? If we have a big compound, and then that has to deal with your electronegativity, or sorry, not electronegativity, the electron domain of your element or of your compound, and the shape that it takes on as it is a compound. So if you look at carbon tetrachloride, CCl4, this compound, when you draw out the Lewis structure, is now symmetrical on all sides. Do we have polar bonds with carbon tetrachloride? Carbon is 2.5 electronegativity and chlorine is 3.5 electronegativity. Do we have polar bonds across carbon and chlorine? Yes, we do. And these all point out towards the chlorine molecule. What shape does this carbon tetrachloride take on? What's the electron domain? Geometry. Good. It's tetrahedral. What is the molecular domain geometry? Good. It's also going to be tetrahedral. Okay. So since we have the same element in all of our spots on our central atom, and all of them are still polar bonds, that means that these are all going to be equal and opposite in the ways that they're poling. And so we make it a non-polar element because all of the bonds are symmetrical. So we have a compound here that is non-polar, but has polar bonds. Okay, if we look at something like ammonia instead, now this turns into something with a lone pair on the central atom. Okay, what is the electron domain for this compound of ammonia? Yep. This is tetrahedral. What's the molecular domain geometry for this one now? Good. So this one's going to be trigonal pyramidal. All right, how I like to remember this one is that I always think of a tetrahedral as like a tripod with something sitting on, with a camera sitting on top. So the three at the bottom, right, are going to be your tripod here. Then you have the camera sitting on top. So that's going to be your tripod. So in this case, the camera is no longer up there. So you just have your 3 feet of your tripod, and that's going to make a pyramid, right? It kind of looks like a pyramid if you can see my fingers and visualize that. That's going to be trigonal pyramidal. Okay. Now that we have a lone pair on our central atom, this now distorts the bond angles. And now there's a electron density that is not being counteracted by something of that's symmetry, right? There's no other symmetry to counteract that. So if we have polar bonds that are all pointing towards our central atom, which
coworkers are shocked.
is this an overall polar molecule?
Your cousin.
I have someone say yes. Yes, it is polar. Because everything's pointing towards the center, it's like you are pushing in here, and that's going to push it upwards, right? This bottom one is also going to push up. So you have all 3 of your feet of your tripod pushing up in this direction. And so overall, your polar molecule and your overall dipole for the molecule will be pointing upwards in the way that you drew it. No matter which way you draw this molecule, right? It will always be pointing where that lone pair is. So someone said, will this be true of all trigonal pyramidal with polar bonds? And this is, right? This lone pair does change it so that your molecule becomes polar, right? It distorts the geometry of the tetrahedral and will cause your element to be polar. So I have a question for the best way to memorize the Vesper chart, and angles, and then, wait, hold on. So I have, before I address one of them, so someone asked, do all lone pairs do that or not necessarily? So not necessarily. There are cases for, right, trigonal pyramidal, we saw where this is now usually a polar molecule with the lone pair, and then bent when you have a tetrahedral is usually polar, right? That's like water. Right? That's going to be a polar molecule. We can have seesaw. We can have seesaw where you have right, something like this, that becomes polar because one of your axial positions is now occupied by a lone pair, and now your symmetry is off. So that is what causes, right? This is another case where a lone pair is now going to cause your molecule to be polar. But then we have square pyramidal. And in this case, you have two lone pairs on your central atom. But in this one, your lone pairs are both in the axial positions, and so those lone pairs being opposite each other create symmetry within the lone pairs. And then the square portion are all the same molecule, all with the same dipole. This causes this element or this compound to be nonpolar. So even though there's lone pairs on this central atom here, this one would be nonpolar. Does that help with some of the, okay, great. So then the person who asked, what's the best way to memorize the Vesper chart and angles? I think that they very much look like the shapes that they're talking about. Or if you can relate it to a certain picture or object that you see in real life, I think that also really helps. Right, so for me, I've been using the tripod. If you can see the tripod, use that, and then you know that tripod is tetrahedral, and you can memorize all of those that way. For the trigonal bipyramidal, which is the 5, that one looks like a triangle with two pyramids, right? You have your equatorial positions of the triangles. Sorry. Right, those are all equatorial, and then you have two molecules on top and bottom of that plane, right? And so you have one up here is Y, one up here is Y. So I think about that as like the triangle base and then up and bottom, right? Top and bottom. And then for the octahedral, that one, I just think of literally the pyramids of Egypt sandwiched onto each other. And then because that has a square bottom and then the two pyramids, right? So I think about that, or like the Sims triangle thing on top of their heads. So if you can relate that to like real world, I think that also very much helps with memorizing the shapes. But a lot of the names really do match the shapes. So if you can look at it that way and kind of visualize that to a real world element, I think that helps memorize them as well. Oh, yep, sorry about that. This one is square planar. not square pyramidal, thank you. Square pyramidal is the one, with just the one on top. So square planar is when both of the tips of your pyramids are no longer there. So in this one here, for the trigonal bipyramidal, these ones are equatorial, right? Because they're going around the equator. And then these ones are axial. And then same thing for square planar. All of these are equatorial. The lone pairs are in the axial positions. In the seesaw, this one is in the axial position. I guess I should change that. This one is in the axial position. And then three of the other elements are in the equatorial position. Any other questions on? That's a great question. So Aiden, yes. In terms of the electron domain 5 and electron domain 6, the lone pairs will come off of the axial positions first. For the set of 5, the electron domain of 5, I think there's one position where you only have two elements and 3 lone pairs. In that case, 2 positions are axial and 1 is equatorial. Let me think about that for a second, actually, that question about the axial positions. Let me think about that and I'll come back to you. Don't quote me on all my words I just said. Because I'm looking at this one now. I believe. Yeah, I totally lied. I was right the first time. So in terms of, it's not an always case. So for your electron domain of 6, your lone pairs are axial first. And that's because all of your bond angles are 90 degrees. And so the best way to minimize repulsion is by removing your axial positions first. In terms of your electron domain of 5, your lone pairs are going to start off from the equatorial position. Because in this case, this bond angle here is 120 degrees, and then this bond angle here is 90 degrees. And so in order to minimize repulsion, you're going to remove the 120s first. And so then it all squeezes towards the other side. So it's not an always going to be axial first. It depends on your electron domain. Sorry about that. Okay. Does that help with electron domain geometries and polar, nonpolar, and all that fun stuff there that we talked about? I had couple people ask about emission and wavelength and whatnot. So we're going to jump to that. Alrighty, so this is talking about this is talking about energy of an electron, right? So at the n=1 state, this is going to be, right, your ground state for a hydrogen electron. Right, but your ground state just means your lowest energy state possible, right? So for some of our multi-electron elements, right, your ground state might be a little bit higher in energy, but the ground state is going to be your lowest energy configuration, right? So that's just adding it up one by one in terms of energy. In order to take an electron from n=1 to n=2, what do you have to do? Are we absorbing or emitting energy here? Good. We have to absorb energy to get from the first energy level to the second energy level. What if we went from 3 to 4? What do we have to do in order to get from 3 to 4? Good. We have to also absorb. Right? We're at a higher energy level if we go up. So we have to take in energy in order to get up to a higher energy level. Now that we're at n=4, I can drop down to n=3, n=2, or n=1. What happens when I drop from a higher energy level to a low energy level? Good. In this case, we're going to emit a wavelength, right? We're going to emit energy. The energy that is emitted is in the form of a photon, right? Okay, so this is emitting energy in the form of a photon. So this is, right, light. This is the colors that we were seeing at the beginning of this chapter, right? They have a specific color wavelength or color pattern for all of the elements, and that's because there are at the energy levels within that element are at certain quantized positions around the electron or around the nucleus. So that electron can go to certain places. So as you drop down in energy, you're going to release that change in energy as a form of light. And so that's where the equation E is equal to hc divided by lambda comes into play. Any questions so far? I think. So as we have energy is equal to hc over lambda, if we have high energy, what does that mean for our wavelength? Do we have a high wavelength or a short wavelength? Good. We have a short wavelength, right? So you have a smaller wavelength. We can see that they're inverse, right? They're on opposite sides. Right, if we multiplied your lambda by energy, in order to maintain those two constants, if energy goes up, wavelength has to go down. Right? In order for the smaller the wavelength, the higher the energy. And if we think about gamma rays, those are your highest energy waves. And these are really, really short, right? They're very, very fast wavelength and they're very, very stuck together. On the other hand, your radio waves are your low energy. And so these have very, very long wavelengths, right? They don't repeat very often. And this is right, you listen to the radio, they have to go around buildings, right? They're so long they can go around buildings in order for you to hear them. Your gamma rays can go through buildings. So they're very short while radio waves are really long. So your low energy is long wavelengths and your high energy is short wavelengths. Yep, and then frequency and energy are direct. So the higher the energy, the higher the frequency, right? Because you see more wavelengths happening more frequently with your higher energy wavelengths. Questions on that? Does that help answer the couple questions about energies? Okay. Right, and just remember the couple equations that you have for energy. You have C is equal to lambda times frequency. You have energy is equal to Planck's constant, which is given to you, times frequency. Right, we combined these two in order to get energy is equal to hc divided by lambda. And then you have the de Broglie wavelength, which is h divided by mass in kilograms times velocity. I believe the de Broglie wavelength equation is given to you, but just in case, that's what that one is. Any other questions on light? Okay. Someone asked about IMFs. These are your intermolecular forces. Then this V here is your velocity. This V here is frequency. And this is mass in kilograms. Okay, so IMFs are intermolecular forces. So for this case, right, couple important things to note is that all compounds have IMFs. What is that called? What is this IMF called? Good. This is dispersion forces. Or London dispersion forces, right? Whatever's easier for you. Dispersion forces is great, or sometimes you see them as LDFs. Right, these are for all compounds. Polar, non-polar, hydrogen bonding, doesn't matter, it will have London dispersion forces. This is because your electrons are always moving, and at some point in time, maybe your electrons end up on the same side of the element or of the compound, therefore creating a high negatively charged portion of your compound, and then a positive charge on the other side, creating an instantaneous dipole, and therefore that causes the other things around it to have a dipole, and then everything interacts that way, right? So all of your compounds will have IMFs, but they are the weakest. These dispersion forces are the weakest. How you can improve dispersion forces is by increasing your molecular weight. So the more stuff you have, right, the more electrons you have, the more possibility that they're going to end up on the same side, creating a larger dipole. So that's why we see that F2 is a gas, but I2 is a solid, right? The dispersion forces in I2 are so strong that they create a nonpolar element to be solid at room temperature. Or fluorine is now gaseous as room temperature because it has fewer electrons to hold together these dispersion forces. Okay. We can also have dipole-dipole interactions. This is when you have polar molecules. Right, so maybe this is trying to think of something. If we have HS, right, this is a polar molecule that looks like this. And so this would have dipole-dipole interactions with other SH molecules that it's around. What's our favorite type of dipole-dipole interaction? What's the special case? What is that called? Yep. Right, we can have hydrogen bonds. And what's the rule for hydrogen bonding? Close. We have must have N, O, or F bonded directly to an H. Okay, so this can be water. This can be ammonia. This could be hydrogen fluoride. Right, all of those have an oxygen, a nitrogen, or a fluorine directly bonded to an H. This is not this molecule here, right? This is not no hydrogen bonding. In a pure substance because there is no oxygen directly bonded to a hydrogen. However, could this molecule bond, or could this molecule hydrogen bond with a water molecule? Yes, yep. This could bond, or could hydrogen bond with water, right? So if it's dissolved in water, then it would hydrogen bond. But if it's just the pure substance of this aldehyde, then it would not be hydrogen bonding. Your ionic bonds are going to be the strongest, and then your hydrogen bonding, and then your dipole-dipole, and then your London dispersion forces. Right, and you can tell if something is going to be polar based off of the shape that you draw it in for your Lewis structure. Remember that for these, this is for covalent bonds that are sharing electrons, and your ionic bonds are a transfer of electrons, creating two ions, and that's why they interact. Okay. Someone asked for question 7. on the mock exam. All right, so question 7 on the mock exam is saying what volume of O2 will be produced by the decomposition of 3.16 grams of KClO3 at 225 degrees Celsius in 0.970 atm. And we're given R and the molecular weight of KClO3. So the important thing here is that we have to do stoichiometry first before we can do our gas laws, right? We're given this is T, this is P. We are solving for volume, and we're given an R. If you're given R, that should be pretty indicative that at some point you have to use PV is equal to nRT. What's the problem though? What units do we need to be in order to solve PV is equal to nRT? Good, we need to be in Kelvin, so this needs to be changed to Kelvin. What else? Good, and we need to be in moles of O2 here. Okay, but we're given 3.16 grams of KClO3. So the first thing that we need to do is say that we have 3.16 grams of KClO3, and we need to get that into moles because we can't convert from grams to grams of things. We need to convert from grams to moles and then moles to moles of each other. So, right, just like we did for exam 1, we're going to take our grams and we're going to use our molar mass to get to moles of KClO3. And then what do you do to get to moles of oxygen? Good, we have our stoichiometry. So for every 2 moles of KClO3, we have 3 moles of oxygen. I don't remember what this is. So we end up with 0.0387 moles of O2. Now we're in the correct units. So now after we convert this to Kelvin, which is 225 plus 273, which is 498 Kelvin. Now we can say that PV is equal to nRT, volume is equal to nRT divided by P. So this is the setup for Pivnert here. And I believe we should end up with a volume of 1.63. Any questions on 7? Does that help with gas laws and stoichiometry? Okay, I had a question about 3. So which of the following statements is true? For A, right, whenever I do a true false question, I always like to prove myself wrong. So for A, the statement says the stronger intermolecular forces between carbon dioxide molecules cause carbon dioxide molecules to behave more like an ideal gas than hydrogen molecules. Right, so we're saying here that the IMFs in carbon dioxide are stronger. For gases, do we want strong IMFs? Do gases want to interact with each other and be held together, or do they not want to be held together? Good, they don't want to be held together. So the stronger the IMFs means that it should act more like a solid rather than a liquid, rather than a gas, right? So the stronger intermolecular forces between carbon dioxide molecules cause carbon dioxide molecules behave more like an ideal gas is false, right? It behaves less like an ideal gas. So A is not it. For B, hydrogen bonding is one of the intermolecular forces between CH4 molecules. Is this true or false? Good, this one is false, right? Hydrogen bonding has to be between HO, HN, or HF. So this one is not it, right? Dipole, this one is actually London dispersion forces, right? Is one of the intermolecular forces between CH4 molecules. That's the only one. This is a non-polar compound, so LDFs or dispersion forces are the only intermolecular forces for CH4. So this is false. And then someone asks, is that why F2 only have dispersion forces for the ideal gases? F2 only has dispersion because it's a fluorine bonded to a fluorine, so there's no electronegativity difference between the two fluorines. And so, right, there's no dipole that's permanent there. It only has dispersion because there's no electronegativity difference. Great question. Okay, so then for C, right, there are no intermolecular forces present between N2 molecules. What is this? True or false? Good. This one is also false. Right, there are no intermolecular forces present. That has to be false. There are always IMFs present. Okay, so this one's wrong, so it has to be D. Perfect. That will 8 cents. Okay, so for 15, we have strontium atoms in a flame emit light with a wavelength of 794 nanometers. When electrons undergo transition between energy levels, what is the energy in joules of the photon with a 794 nanometer wavelength? So for this one, there are two ways that you can do this. One of them combines the equations and one of them doesn't combine the equations. So in this case, right, you're going to be like the two equations that you need to know are that the speed of light, or c, is equal to lambda times frequency. And then that energy is equal to Planck's constant times frequency. You can combine these two to say that energy, right, you can solve it for frequency is equal to c divided by lambda. You can plug this in for this. So you get energy is equal to hc divided by lambda. And then you're actually given everything from the equation, or from the question here to plug into this equation. So you're solving for energy, which is in joules. You're given this constant. You're given the speed of light. And you're given your nanometers, which if you convert that would be times 10 to the -9 meters. and then it can just solve directly for that. If you're given something in nanometers and you're trying to solve for energy, your energy should be about something times 10 to the negative 19 joules. Right, so if you get about that range, then you probably did it correctly. In this case, this is 202.50 times 10 to the negative 19 joules. Right, so that one is within the range of 10 to the negative 19, so that's good to go. But that's how you would solve 15. A couple people have asked for chapter 8. I honestly don't remember what chapter 8 is, so just remind me what that is and I will go over it, but like something specific from chapter 8. They all blend together, I'm sorry. Okay, and then the last question I got so far from the mock exam was the Lewis structure for 8. So we're going to solve, right? We're going to go through our steps of a Lewis structure. The first one is to find our valence electrons. Oxygen has 6, chlorine has 7, and we have 2 of those. So we have 6 plus 14, so we have 20 valence electrons. We're going to draw our skeletal structure now. We have 1 oxygen and 2 chlorines. So even though oxygen is our more electronegative element, we're going to put that in the center because there's only 1 of them. So we'll have oxygen in the center bonding 1 time to chlorine. So if we have 20 valence electrons, we just used 4 from our 2 bonds because every single bond has 2 bonds between them. So we use 4 electrons here. So now we have a total of 16 left over. And we're going to give that to our chlorines first. We use 12. We now have 4 electrons left over. And we're going to put those on our central atom, right? It's not like we ran out of electrons. So we don't need to be making any double bonds. We just have extra. And those are going to go to our central atom because it didn't fulfill its octet rule yet. We're now asked to find the best Lewis structure so the first thing you're going to do when you're asked to solve for the best Lewis structure is to calculate the formal charge. And your formal charge is the valence electrons minus the number of non-bonding electrons minus one-half bonding electrons. So in this case, if we're solving for this chlorine here, formal charge is going to be equal to 7 because it has 7 valence electrons from the periodic table. It has 6 non-bonding electrons, 3 lone pairs that each have 2, minus 1/2 of the bonding electrons, which is that single bond. And then you have 2 electrons there. So the formal charge on chlorine is going to be 0. The chlorine on the left looks exactly the same as the chlorine on the right. So this is also a formal charge of 0. And if we solve for the formal charge of oxygen, we have 6 minus the 4 non-bonding electrons minus the 1/2 of the 4 bonding electrons from the 2 single bonds. So your formal charge here is also 0. So in this case, the original structure that we drew has minimized formal charge where all of our elements have a formal charge of 0. All of our octets are fulfilled and all of our formal charges add up to the total charge of our element, right? There's no charge on OCl2 and none of our formal charges have a charge. So this is going to be our best structure. So that's how you would solve for the best Lewis structure. Okay. Someone asked for hybridization, so if we look at this question here. Right, question A asks for what is the hybridization on the starred element? So your starred element is carbon in this case. When you're looking at hybridization, you're looking at how many electron domains there are. How many electrons domains does the carbon have here? It has 3, right? The double bond counts as 1 electron domain. It's stuck between the carbon and the nitrogen. So there's 1, 2, 3 electron domains. That means you need 3 hybrid orbitals in order to determine its hybridization. So in this case, you're always going to start off with an S, and then how many p orbitals do we need? Someone said it directly to me in the chat. Good, we need 2. So it's going to be sp2. What about this carbon here in the box? How many electron domains are there? Someone already answered, right? Eric gave me the hybridization. This one has 4 electron domains, which means it has an sp3 hybridization. If we look at carbon dioxide, what is the hybridization orbitals of carbon dioxide? Good. This one, it's just sp. We have 1, 2 electron domains. So we need 2 hybrid orbitals. That comes first always from the s and then 1 p orbital. So it's just going to be sp. Right? We could have something where it was this guy here. How many electron domains are on phosphorus? Good, there's 5. So our hybridization is now going to come from the s orbital first. How many p orbitals are there? Good, there's 3p. Can we do sp4? No, we cannot. So we have to go to the d orbital next, right? So the hybridization on PCl5 is sp3d, and that's 5 total orbitals for the 5 electron domains that we have. Does that help with hybridization? Okay, and then this will probably be the last questions we have time for. So to quickly go over mock exam 6, pretty similar to the one below it in terms of like PV is equal to nRT. But in this case, you're saying you have laboratory conditions at 1 atm and 25 degrees Celsius. You have a 6.54 gram sample that has a volume of 5 liters, and you want to know the identity of the gas. Here it's important to remember that this comes from your molar mass. And your molar mass is in units of grams per mole. You're given a pressure, you're given a temperature, you're given a volume. You're always given R, so you can use PV is equal to nRT in order to solve for the number of moles you have from this gas sample that you have. Your N that you solve for is in moles. So then you can take your 6.54 gram sample and say, okay, I have 6.554 grams divided by the N value that you have in moles, and now that's in grams per mole. And that should correspond to one of these guys here. I do believe it is oxygen, if I remember correctly. So maybe you can prove that to yourself as like a little extra practice. Right, just identity comes from molar mass, which is in grams per mole. So you're going to use PV is equal to nRT in order to get moles, and then use that with your gram sample that you started off with. Alrighty, any other questions? Did we cover all the chapter 8 material that people wanted to cover? Yes, so I do believe that it should be, yes, 6.54 grams divided by N is equal to PV over nRT. Yeah. Okay. So for question 12, right, you have supposed that 3 unknown pure substances are liquids at room temperature. Make vapor pressure measurements to find that the substance Q has a pressure of 110, R has 42, and S has a pressure of 330. Which substance has the highest boiling point? This is telling you that vapor pressure and boiling point are related to each other. Right? Think of boiling point as the ability for that substance to get into the gaseous phase. So if it's easy to get into the gaseous phase, then the boiling point is going to be lower. So at room temperature, more particles will be in the gaseous phase. So your highest pressure here of 330 torr is saying that this has the lowest boiling point because it most easily gets into the gaseous phase, right? So at room temp, 22 degrees Celsius, a lot of it is in the gaseous phase. At 42, but for 42, this one is saying that you have really low vapor pressure, which means it's harder for the substance to escape into the gaseous phase because your boiling point is lower, probably due to IMFs, probably due to size, right? Other factors that we've talked about. So the thing with the lowest vapor pressure has the highest boiling point because it's the hardest to escape into the gaseous phase. So in this case, it's R. We talked about that briefly at the start of class today, with like the phase diagram, or not the phase diagram, but the diagram with all of the, like this is 760 torr, right? And you had your different substances going like this. At what temperature? This was temperature that they boil. Does that help? Question 12. Okay, well, that is 8 o'clock. If you have any other questions, please feel free to email me or, yeah, I guess email me because I won't see you before the exam. Please feel free to email me, send me a message in the group me if you're in Dr. Altman's or Dr. Altamos's class. If you're in Dr. Altman's class, feel free to watch this, come on Wednesday and ask more questions. The answer key for this mock exam should be posted. And if you need any other study tips, feel free to let me or Dr. Altamos know or Dr. Altman know, and we'll be happy to help you. Right, find some questions or, point you in the direct equation or the direct direction for your questions. Good luck on your exam, right? You have this one and then your final and you're done. Make sure you get a good night's sleep, and Remember, if they ask you to rank something, pick your extremes as the lowest and the highest, right? Don't ever pick something in the middle if you're asking for an extreme. And remember, it's always about the electron. And good luck. You're going to do so great. You've put in a lot of effort. Thank y'all for coming. Y'all welcome. Thank you.